Welcome back. This is the second session on continuous logarithms on the set of non-zero complex numbers. So yesterday we showed that there exists no continuous argument on C star, that is a set of non-zero complex numbers. And we also identified the root of the problem seems to be when I go along a circle, start at some point and come back to the same point, going along the anti-clockwise direction, it looks that as though there is a jump in the argument. I have to add a 2 pi extra. Okay, that gave us an idea. Maybe I could remove one point and look at the circle. Okay, a circle minus a point on the circle, and we wondered whether on that set can we give a continuous argument. Okay, that's what we want. We said yesterday. We will prove it today. Okay, so let's start screen share. Yeah. So what we said was the following: fix an alpha a real number and define S1 alpha to be the set of in S1, that is mod z equal to 1, and z is not equal to e power I alpha. Alright, then we wanted to say the map phi, which is alpha to alpha plus 2 pi to S1 alpha, defined by pi of t equal to e power I t, is a homeomorphism. Is a bijection, and it's continuous, and the inverse is also continuous. The single word is pi is a homeomorphism. Okay, this is what you want to prove today, right? And let's just make sure that everything is fine. Okay, right. Okay, now, so we had already proved phi is a bijection, done, and continuous done, and so I only have to say pi inverse is continuous to prove. This is what you have to prove. So what does that mean? So suppose Zn belongs to S1 alpha and Z also belongs to S alpha, so that Zn converges to Z, then I want to show phi inverse of Zn converges to phi inverse of Z. This is what I have to check, right? Okay, now remember, since phi is a bijection, Zn is e power I Tn, where Tn lies in alpha to alpha plus 2 pi, and Z is also e power I t, and t also lies here. So therefore, what is phi inverse of Zn? Phi inverse of Zn is by definition Tn, and phi inverse of Z is t. Therefore, question is, does Tn converge to t? This is the question. We have to prove that. Yeah, make sure you understand this. Pause, review, proceed. Okay, now the proof is very interesting. Okay, notice that I want to show Tn not only converges, I have to say Tn's are where they are in the interval alpha to alpha plus 2 pi. So I have to show Tn not only converges, it converges to t, right? So what do you think should be the best way? You can say that I want to estimate Tn minus t in modulus, but that will be difficult. So the trick is beautiful. It's a very nice exercise after Bolzano-Weierstrass theorem. What does it say? if Zn is any bounded sequence of complex numbers, then it has a convergent subsequence. Right? So as an exercise based on that, we have the following. Let Zn be bounded sequence, then Zn is not convergent if and only if there exists two subsequences which converge to distinct limits. Distinct or different limits. See, just try to understand. This is a beautiful thing. I don't find it in textbooks, but in my real analysis and complex analysis I have given this. I think actually I have proved them. Okay, I have solved this. It's not an exercise, it may be more a proposition. Okay, so if I have a bounded sequence, suppose it's convergent, I know that every subsequence will converge to the same limit. Right? Now if I have a bounded sequence, to show it is not convergent, okay, what all I have to do is I have to find two distinct subsequences which converge to distinct limits. Okay, your standard example, alternating sequence 1 minus 1 1 minus 1, the subsequence consisting of odd numbers will converge to 1, the subsequent consisting of even indices will converge to minus 1, and hence we know the original sequence is not convergent. Right? And it's an if and only if. Right? We will come to the proof a little later. Okay, so let's go back. So I want to make use of this exercise. Now what is that I want to prove? I want to prove Tn converges to T. How I plan to do is something very interesting. I plan to show that since the Tn is bounded sequence, because it lies in the interval alpha to alpha plus 2 pi, okay, take any subsequence, suppose it converges, okay, then I will show the limit is T. You understand that? Take any subsequent T and K, assume it converges to some S in alpha to alpha plus 2 pi, okay, that S must be T. Okay, therefore what do you think I have proved? Go back to the exercise. Therefore the sequence has to be convergent. Right? Next, what are you following? The sequence Tn must be convergent because any convergent subsequence has a limit T. Therefore the original sequence Tn must be convergent. And where will it converge to? It has to converge to T, because any subsequence of that already converges to T, and therefore the original sequence Tn also must converge to T. You understand that? This is the idea of the proof. Please understand. Okay, learn this well, because this is not usually done. This is beautiful exercise, is not done, so learn this well. Okay, now how do I prove that? So let us assume, okay, a subsequence T and K, okay, of Tn converges to S. Now where is Tn? Tn lies in the interval alpha to alpha plus 2 pi. Therefore, since T and K is convergent, the T has to be in the closed interval alpha to alpha plus 2 pi. Okay, it may not be in the open interval. Sorry, yes. Yes has to be in the open interval. Yeah? Okay. Now what are the things I want to do? First, notice that since the T and K converge to S, e power I T and K converge to e power is. This is by continuity of exponential map. Right? T and K going to I T and K, that going to exponential I T and K. Okay. As I said yesterday, I will write exponential I T and K as e power I T and K. Okay? Right. But notice that e power I T and K, this is a subsequence. Subsequence of what? e power I Tn. And what do I know about e power I Tn? I know it converges to e power It. And this is a convergence subsequence, but this converges to e power Is. Therefore, what is the conclusion? By the uniqueness of the limit, I know e power Is must be equal to e power It. Yeah? Okay. Very good. Now, let us look at it. Now, where is t? T is in the interval alpha to alpha plus 2 pi. Right? And S is in the interval close to alpha to alpha plus 2 pi. Right? Now, what are the things I know? This S cannot be alpha and cannot be alpha plus 2 pi. Why? Because if it is, remember our first one in the proof, we proved the map phi of t equal to e power It is a bijection of alpha to alpha plus 2 pi open onto S1 alpha. This is a bijection. Yeah? Right. Therefore, and also notice that if S equal to alpha or S equal to alpha plus 2 pi, then S power Is is same as e power I alpha. You follow that? Yeah? Right. But then what does that mean? But e power I, therefore e power I alpha equal to e power It, whereas t is in the open interval alpha to alpha plus 2 pi. But we have seen on this is 1 1. Therefore, this is a contradiction. That is phi of alpha equal to phi of t. This is a contradicts 1 1 nature of phi. Right? Therefore, we conclude S is not alpha, S is not equal to alpha plus 2 pi. Understand this? Okay, good. Now what do I have? S is not this. Now therefore S has to be in the interval alpha to alpha plus 2 pi. But then I have e power Is equal to e power It, and t also lies here, and my map, this is phi of S and phi of t, and phi is 1 1 on a bigger interval. Therefore this implies S equal to t. So what I have shown, if t and k is a convergence subsequence of Tn such that t and k converge to S, then S is nothing other than t. Okay. Therefore, what do you think I have proved? I have shown that therefore, what do you think I have shown? I have shown that any convergence subsequence of Tn converges to t. You understand that? Therefore, I cannot find two convergence subsequences which are converged to distinct limits. Therefore, by the exercise which I just now quoted, okay, the original sequence Tn, bounded sequence Tn must be convergent. Very good. So its convergence is okay. But why should it converge to t? That's also clear, because Tn is convergent, we have proved, and it's a bounded sequence, therefore it has a convergent subsequence t and k. But any convergent subsequence t and k converges to t. But since Tn is also convergent, these limits must be the same. Therefore, Tn must also converge to t. Do you like the proof? Enjoy that. Okay. So we have proved phi inverse is continuous. Right? Okay. Please understand. Take some time. Okay. So we have shown that the map from S1 alpha to alpha plus 2 pi and okay, going to t is continuous, and we got the map phi from alpha to alpha plus 2 pi to S1 alpha is a homeomorphism or if you don't like that, bijection continuous and pi inverse is also continuous. So we have proved the result. Okay, go through the proof. I'm sure all of you will love this proof. You may not have seen how Boltzmann-Weierstrass theorem can be used in such a subtle way. So what have we achieved? We have achieved, even though I may not be able to find a continuous argument on this, okay, there exists a continuous argument on s1 alpha for any alpha real number. So that means you start with this and remove 1 alpha. This is e power I alpha. Just remove that. So for all the rest of the things, I am happy. Okay, for all these things I have continuous map argument. Okay, now how does this help me? Okay, now let's look at define R alpha to be the set of complex numbers in C star non-zero real such that z by mod z is not equal to e power I alpha. That means you fix an alpha. Okay, so this may be my alpha, this may be my alpha, and this is my R alpha. Okay, this is the angle alpha. Okay, maybe I should have used a different notation. This is a ray, so this is a half ray or ray. Okay, through e power I alpha. Alright, that's simply saying z is not of the form some r times e power I alpha where r is positive. Remember, z is non-zero, therefore r cannot be 0 anyway. So this r alpha, now let's look at u alpha to be c minus r alpha. Notice that this is one open set C star. Okay, this is an open set in C. Why is that? Because what are we deleting? We are deleting r times e power I alpha as r is greater than or equal to 0, alpha fixed. Okay, this is a closed set. Right, e power I alpha is fixed, therefore if I have a sequence r and e power I alpha which converges to r e power I alpha, okay, cancelling r for since r and are greater than or equal to 0, r is also greater than or equal to 0, therefore this is again an element of the set. Okay, so I am actually proving it's a closed set. This is for those people who do not know how to check such things. Okay, make sure you understand this. Right. Okay, right. Now let's come back. So I want to say there exists, so the final result is the following theorem: there exists a continuous argument not on C star, on u alpha. What is u alpha? From C star I remove one open thing. Maybe I will say r alpha greater than or equal to 0. Okay, do you understand this? So what does it mean in this? Okay, I remove one alpha, this is alpha, this is my r alpha, I remove that, and the rest of the things I am happy. So I have continuous argument on the, if I remove the half ray. Okay, now I want to prove that. Okay, so the proof is very easy. Start with z in u alpha, then z going to z by mod z. Okay, remember z is not equal to 0. because 0 is removed, right? U alpha is a subset of C star. This is okay. And where does this belong to? It belongs to S1. Okay. And since Z by mod Z is not equal to e power I alpha, it actually belongs to S1 alpha. And from S1 alpha, I have the P inverse map. That is continuous. Okay. Therefore, this I can write as e power it for t lying between alpha and alpha plus 2 pi. Okay. Therefore, this goes to t. Okay. If e power it, then this goes to t. Okay. Now this is a continuous map. This we proved is continuous map. Therefore, this is continuous map. Therefore, the map z going to, or let us say phi inverse of z by mod z is okay. Z going to this is continuous, right? Okay. And where is this map? If you want to call this map as theta alpha. So theta alpha of z is, look for z by mod z, that is in S1 alpha. Look at phi inverse of this. Okay, this is a real number. Therefore, theta alpha is from C star minus R alpha, which is my U alpha, to R is continuous. I claim this is an argument. Theta alpha of z is an argument. And of z. Why? What is that I have to prove? I have to prove z is mod z into e power I theta alpha of z. This is what I have to check. Okay. This is very easy, but I will certainly go through a proof. Remember, what is theta alpha of z? Phi inverse of z by mod z. Okay. So this is your t, right? Therefore, what is the meaning of this? This happens if only e power it equal to z by mod z. But that is if only if z equal to mod z into e power it. Therefore, this is an argument, and the map z going to theta alpha is continuous. Okay. So what have we shown? So we had proved that we cannot find a continuous argument on the entire C star, but if you are ready to sacrifice, ignore one half ray through the origin also included, throw it out, that closed set, what I get is an open set. On that open set, I can define a continuous argument. Okay. For what kind of continuous argument? For each alpha in R, I can define an argument. If you want to rest it, you can also say something like closed at 0, open at 2 pi, because anything can be brought into this. Okay, I will come to that in a minute. So I have proved the existence of continuous argument. This is what I said yesterday, right? If I know I have an incurable disease, I learn how to live with that comfortably. Okay, you will see this, how to do that as we go along. Okay, therefore for each alpha I have this. Now suppose I have two such a thing, phi alpha and phi beta. What is the relation between them? What does that mean is e power, therefore z equal to mod z into e power I phi alpha of z is also equal to mod z into e power phi beta of z, right? And mod z is not equal to 0, therefore this implies e power I phi alpha z is same as e power I phi beta of z. So by periodicity I know phi alpha of z minus phi beta of z is some 2n pi, right? Okay. And this, you may think this n depends on z, but remember u alpha is actually a star shaped set, and in particular it's connected, right? and therefore this n may depend upon n of z. Therefore this is call this as psi. This function psi is a function from u alpha to r, taking values for every z. This is an integer, right? And since this is connected, if those of you who have not learned the such things may ignore, then this is connected, okay, this must be pi of u alpha must be a connected subset of r, right? Therefore since it takes values in z, it must be a constant. So we know it is our single n. There is a single n as an integer so that pi alpha and pi beta differ. That is, unit to continuous arguments on u alpha differ by a constant. What is the constant? 2n pi. Okay, please understand. And if you don't like connectedness etc., what all you have to do is this. Suppose I have fixed alpha, right? Then you can see from take something point like this, then any point will be connected to a line here. Right? So if I restrict psi, if I restrict psi to this, okay, this must be a constant because this is connected, this is like a line, right? Therefore I can use intermediate value theorem, therefore I can conclude it must be a constant. That constant must be this, and but every point here can be connected by this kind of line segment. Okay, if you learn connectedness, it will be easier, especially if you have gone through my lectures on connectedness, you will find it easy. Okay, otherwise just assume, right? So we have proved this. Now what have we achieved? Okay, so like yesterday we proved unit to continuous argument on S1 differ by a constant 2n pi. Here also we proved the same thing. Both the cases dependent only on connectedness concept and continuity. Okay, the next thing, I will just start with that, but we will continue later. Okay, how does this help me? Now suppose I have u alpha, from u alpha to c, okay, now I can define z going to square root z, a continuous function, or z going to z to the power 1 by n, a continuous function where n is a natural number. Okay, do you remember this is one of our motivation in the first session? Why it can be done? Because let us look at theta alpha to be the continuous argument on all u alpha. Okay, this is argument, not average, because my r looks like v. Yeah, right. Therefore any z is mod z into e power I theta alpha of z. Therefore I can define square root of z to be the unique non-negative square root of mod z into e power I theta alpha by z, the whole thing divided by 2. Okay, now you know this map is continuous. Okay, therefore this going to square root z. See, z going to mod z is continuous. Okay, this is from u alpha to r, this is actually positive, non-negative, and here going to square root, this is continuous. Therefore this is continuous. Yeah, and next, what do I know? Z going to I theta alpha z by 2, this is continuous, and that followed by exponential map e power I theta alpha z by 2, this is continuous, and therefore this is a product of two continuous maps. Therefore I have defined square root map as a single valued map. Okay, it's a function, therefore I should not say about that, right? Anyway, it's a continuous function, but I have not defined on all of C star, but I have defined only on u alpha. Okay, and this can be done for each and every u alpha. Yeah, so we have done that. Okay, in the next lecture what I will do is we will show how this helps us to define a logarithm. Remember, in real numbers, okay, you learn how to work with, because of calculus, exponential, logarithm, and trigonometric function, hyperbolic function, you know how to work with them, but you may not have learned rigorously, many of you. So exponential map on R is a continuous bijection of R onto positive reals, right? It's therefore the inverse exists, that is also continuous, because increasing function, the inverse image of this increasing continuous function will again be continuous for various reasons. That is called logarithm, right? Therefore the unique t says that exponential of t equal to x is called the logarithm of x, t, then you denote by t by log x. Okay, that's why you define, and it's unique, right? So how will I like to define logarithm on complex numbers? First remember, okay, I cannot define logarithm of any number. I have to define only logarithm of positive numbers. Here I have to define logarithm of complex numbers. How will I define? Suppose you pick an alpha, okay, a non-zero number. Remember, exponential maps C onto C star, onto non-zero real number. Therefore, if you give me any alpha, it is of the form exponential z for some z, but there may be many z. So any just z I will call as logarithm of alpha. Now guess what should be the next question? Yes. Okay. Can I choose continuous logarithm on C star? I'm sure you know the answer. We will attend to this in the next session. Okay. Have a good day. I hope you all liked it. Go through the proof. Okay. Where I proved phi inverse is continuous. You will love that.